In the last few episodes, we've talked about multiphase form material balance in Whitson Plus. And in a nutshell, it's fairly straightforward. It's a method that doesn't require relative permeability, so it only requires PVT and production data. It outputs the pore volume, or when you mix that with PVT data, you can output your OIP that you can use to guide other types of analysis, such as numerical RTA. The diagnostic plot itself is fairly easy and straightforward to interpret. You're just picking a slope through a wide range of data, and then the inverse of this slope is an estimate of your pore volume or your OIPs. Which means that this slope would be a small OIP, this would be a big OIP, and this will be an even bigger OIP. But when you deal with real data, a lot of people look at the diagnostic plot and say, yeah, but here I see different slopes, multiple different slopes actually. So when you work with real data, the question is which slope should you actually pick? And that's where this associated plot to the right here, this pressure plot that you also see in Whitson Plus up here to the right, that they can also maximize, becomes very, very important. Okay, so the gray dots here, that's the bottom hole pressure versus time, so that's measured data, and the plot to the left is essentially just made up by PVT and production data, and of course it leverages bottom hole pressure versus time. Then the first slope that you see on the plot is something similar to slope number A. That's made up typically in a period here before you go two-phase, and if you pick that slope, estimate that, and use that as your pore volume, and you back out your average pressures versus time, you will see this yellow line, or this yellow average reservoir pressure versus time in this associated plot here to the right. And then you might see this transition period, which you very, very often see in this diagnostic plot, the slope number B. But if you use that slope, you'll end up with an average reservoir pressure estimate versus time that's actually below your measured bottom hole pressures, which definitely doesn't make sense. There has to be a delta between your average reservoir pressure and your bottom hole pressure that's positive for you to have any production. And we know that this well is producing fluids even after whenever this intersection here is happening. So slope number B is obviously a too small of a pore volume. Then we see the slope number C here, which is probably in a more stabilized portion of the data late time, and if you use that portion of the data, that results in this average pressure versus time in the software, and that the software automatically spits out when you click run. Okay, and in this particular example, this least shallow slope would be the largest pore volume that you're seeing as a part of the diagnostic plot right here, and you should, as a general rule of thumb, pick the shallowest slope observed when the largest pore volume is observed. Okay, so if you're picking the shallowest slope on the graph to the left, you're essentially picking the largest pore volume observed, at least until that point in time in history. Okay. Another special case is if you're dealing with buildup data. So if you have buildup data present, okay, and in this particular example, you see that you have a buildup period right here, and this data is from a gauge, so we know when we have a lot of confidence in the gauge data right here. So we know that these are legit buildup data versus time. And then we have the associated diagnostic plot here to the left, where the slope number A gives us this average reservoir pressure estimate versus time, which is obviously too conservative because we go below the measured bottom hole pressures versus time. And then we see this more stabilized portion of the data that we could at least anticipate would be a good estimate of our pore volume. But what we see here is that it is above the measured bottom hole pressures versus time, but it actually intersects the bottom hole pressure during this buildup period. Okay, and in these scenarios where you have buildup data, it's very, very important that you leverage this type of data and put a lot of emphasis on it. And actually in this scenario, you would have to go to a slope C that actually doesn't intersect with your data, but that assures that you have an average pressure that at least intersects this data, if not is higher, such that you get a consistent average pressure estimate versus time compared to your bottom hole pressures. Okay, and then you might say, but yeah, but the diagnostic plot to the left is not exhibiting this type of slope, and that's true. So it's not exhibiting that type of slope yet. So when you're just using pure depletion data, it's not observing that pore volume yet. But if we gave this well even more time, we would eventually see it at least falling onto a slope something similar to this. So that leads to kind of the second observation, that if you have buildup data present, then adjust your slope until it honors the buildup data, and the slope might be shallower than what the depletion data only suggests. And a shallower slope means a higher pore volume. Okay. A little bit relevant to this, if you have frac hits in your data, or so-called bashes, and you can see that in your bottom hole pressure, then you should be a little bit careful when using the interpretation technique that I talked about earlier. And the reason for that is that, you know, the fact that you get higher measured bottom hole pressures during a bash is not due to a true reservoir pressure buildup, but it's due to essentially interference between an offset well and the well that you're analyzing. So in this case, you should then ignore that part of the data, which you very easily can actually do inside of the software by using this exclude point right feature right here in the software, and that will automatically then ignore that part of the data on the diagnostic plot. Okay. The last thing to also emphasize is that if you're dealing with a well that's still infinite acting when you interpret it, then you haven't seen all the pore volume yet. So that means that your interpretation will be conservative. So if we look at the diagnostic plot here to the left, and where we only have seen in the short period of time these blue little dots here to the left, and we draw a slope through that, we estimate a pore volume around 500,000 barrels. If we give it a little bit more time, we see that our curve here is starting to bend over, and our slope is starting to get shallower. And if we draw a slope through this data, the OIP that we estimate is 2,000 barrels. Okay. And if we actually allow it to reach and see all the boundaries, so it reaches true pseudo-steady state, then we're actually seeing the entire tank size in this case, which is 3.4 million barrels, which is exactly the same as the actuals. And you see here as well that this is an infinite acting period, and this is the, call it, more boundary dominated period, which leads to one of the key conclusions, that if you are still infinite acting, or at least if some part of your reservoir that you're draining is still infinite acting, it doesn't have to be all of it. You might see some boundary effects, and you might still be in a transition period, but at least if you have some parts of the reservoir that you're draining that's still infinite acting, your estimates will be conservative. Okay. So that leads to these four conclusions: that you should always pick the shallowest observed slope in the data set. That will be the largest pore volume observed to that point in history from that well. If you have buildup data present, make sure that you adjust the slope until it honors the buildup data. There is transients in the buildup data that can be captured more quickly by the buildup itself than what you can see from just pure depletion data. And if you're dealing with a frac hit, this part of the data should be ignored, or at least be interpreted with a lot of care. And if your well is still infinite acting, then the multiphase flow material balance procedures will provide you with conservative estimates of the pore volume. That can be all the different pore volumes. And you can then use another technique like numerical RTA, for instance, to evaluate whether or not your well is still infinite acting or not.